Hi guys, today I want to take a look at the formal definition of a limit, right? So what do we mean when we say a limit, usually? Usually, in the informal way, for example, in the AP Calculus course in America in Canadian high school, when you've been taught the idea of limit, is more like, if I summarize it up, is the as in this case what we have here is that if our x get close to a, then our f of x get close to L. That's what usually the limit mean when you're doing like Calc 1 with no formal definition whatsoever of a limit, right? If you look at this diagram, what limit mean is that as the x approaches, the a, the the f of x approaches the value L, right? So that's what we mean when we say by limit. So now our mission is that we want to take this and then turn this into a mathematical definition or a mathematical sentence that we could use to prove that limit exists. So how will we do that? Well, let's look at our first part. Well, our first part says is that if our x get close to a. So how do we translate that into mathematics, right? So the first step would be that you will want some kind of expression that links the relationship between x and a. And we do that by writing absolute value of x minus a. So what does this exactly mean? Well, this means the distance between x and a, right? So for example, if we zoom in on what we have on the left, and this is a, right? And we have our x here. If we take the absolute value of x minus a, in this case, well, if x is smaller than a, it might be negative. That's why we have the positive. That's why we have the absolute value. If you take absolute value of that expression, it's going to give you the distance between x and a, right? So it kind of makes sense is that if we want to express the sentence in a mathematical way, we first need a way to describe the distance between x and a for we to say that we want x to get close to a, right? So let's erase that. So x absolute value of x minus a is the distance between x and a. So now we have successfully linked x and a. Now the next part is that how do we describe that we want x to get as close to a as possible? So how do we do that? Well, we do that by saying that it is smaller than some kind of symbol, which we call delta, that you'll see. Well, like you might ask, then why don't we just use some numbers? Like for example, you could say that x minus a is smaller than 0.01, right? So why would that not make sense? Because the reason is because you could always find a smaller number than 0.01, which would also work for this case, right? Because if you want to turn the sentence, our original sentence is that our x get as close to a as possible, which then if you translate that, that means that we want the distance between x and a to be as small as possible. So you want a number that is bigger than this distance between us to express the length of the distance between x and a, right? But like if you use 0.01, it really doesn't make sense because you can always find a smaller number, which is 0.01. Then the distance between x and a will be way closer than 0.01, right? So the problem is you can never find a smaller number in mathematics, right? If I asked you to find any number that you can think of right now, you could almost all guarantee that you could always find a smaller number than what you just thought of. So therefore, it doesn't make sense that we use some kind of number such as 0.01 to represent the distance between x and a, because we want like an arbitrary idea of a number, like a really, really small number in this case. This is why we use this thing called delta, because there's no way that you find any smallest number, right? Because that doesn't really even exist. So we use delta here to represent a small quantity, right? And then we also have to make sure another thing is that our distance between x and a is always bigger than 0. So we add that to our inequality right here. Is that what does that mean, right? Well, if the absolute value of x minus a, in another word, the distance between x and a is always bigger than 0, it would mean that x would never be equal to a, which is what we want in this case, right? Because the whole idea or definition of a limit is that we do not want x to be on a, we want it to approach a, right? So therefore, by adding this inequality of bigger than 0, we exclude the possibility of it being equal to a, which is what we do not want. So we have done the first part of the formalizing part, and then now we get to the second part. Well, if our x get close to a, which is the absolute value of x minus a is bigger than 0, smaller than delta, which in that case delta means some kind of small arbitrary thing that you have to remember. And then remember, this is if you have watched my previous video, I have talked about like an if-then statement. In this case, it is right because we have an if and we have a then, so it can be expressed in some kind of px implies qx way. In this case, our qx would be that then our f of x get close to L. So how do we translate that into a mathematical definition? Well, we do it first. Again, the same idea is that you want to find some way to link f of x and L. In that case, we're going to do it the same again, which is that f of x minus L is smaller than some number epsilon, right? So what exactly does that mean? Well, absolute value of f of x minus L is the distance between f of x minus L, of course, the same case as x minus a. In this case, we also want to say that they get the distance between them is really close to each other, but following the same logic that I've talked about, there's no smallest number you can pick. So we have to choose some arbitrary value, epsilon, which is like a representative of a idea of a small, right, to replace any number that you can think of. So in this case, this will be our formal definition of a limit. But we're missing a quantifier here, which is that I'll add it to this. For every epsilon bigger than 0, there exists a delta bigger than 0, such that 0 is smaller than x, the absolute value of x minus a is smaller than delta. It implies that absolute value of f of x minus L is smaller than epsilon. And then, yeah, so this will be our formal definition of a limit. And then you could try to use this definition. I'll show you in my next video how do you use this definition to prove a limit does exist for an example function. So that's it. That's your formal definition of a limit. And then, yeah, so thanks for watching.